Imagine that you had a truck full of 7,000 kilograms of apples. Right, so that's a lot of apples. You want to estimate how many apples are in that truck. You know that a dozen apples of that type have a mass of 2.0 kilograms, and also that a dozen apples is 12 apples. So you want to go from kilograms to the number of apples. You want to convert from kilograms to the number of apples, but you don't know the mass, the number of kilograms in one apple, only the mass of a dozen apples. So to go from kilograms to apples, you need to go through a rest stop unit, dozens of apples. And so, that has a relationship to both kilograms and to the number of apples. And so that can connect kilograms to apples. So you can start out with the certain number of kilograms and having that on top and bottom. That can cancel as you go into dozens of apples. And then having dozens of apples on top and the bottom, it will cancel, leaving you a certain number of apples. This dozen apples, this 12 of something, 12 is a dozen. This is a lot like the unit the mole, which we'll use all of the time in chemistry. A dozen is 12 of something, but a mole is 6.02 times 10 to the 23 of something. That seems like a pretty weird number. Where did we come up with that? Well, it's derived from the fact that 1 gram has a mass of 6.02 times 10 to the 23 atomic mass units. Recall that an atomic mass unit is the mass of a proton or neutron approximately. So this number, you're going to be dealing with it all the time. We even gave it a name. This is Avogadro's number. So we have 1 mole of something, of anything, is equal to 6.02 times 10 to the 23 of anything. It could be, you could have a mole of cherries or a mole of basketballs. But in chemistry, though, we're going to have 1 mole of representative particles is equal to 6.02 times 10 to the 23 representative particles. And now representative particles can mean kind of 3 different things. It can be atoms, like if you're dealing with just individual atoms of an element, like neon floats around as a gas all on its own. Or you can have 6.02 times 10 to the 23 molecules in a mole of molecules. Molecules are when you have 2 or more nonmetals bound to each other, or nonmetals and metalloids. And then you have compounds as well that are not molecules. We don't call them molecules because molecules have covalent bonds within them, which occur between nonmetals and nonmetals. So if you have something which has a metal and nonmetal, like calcium and chloride, then we call that a formula unit. It's just a small unit of that ionic compound. So representative particles can mean any of these 3 things. All right, so let's see if we can do a conversion. Let's say that we had 1.24 times 10 to the 24 methane molecules. Now methane is natural, the main component of natural gas. We use it to heat our homes, we power our power plants, many of them, and heat our stovetops, some of them. So if you have this number of molecules of methane, how many moles of methane molecules are there? So you've got this number of molecules, a certain type of representative particle, and so there are 6.02 times 10 to the 23 of molecules per mole of those molecules. There's 6.02 times 10 to the 23 representative particles per mole of representative particles generally, or molecules specifically. So having methane molecules on the top and bottom, that'll cancel. So we have 1.24 times 10 to the 24 over 6.02 times 10 to the 23. And when you plug that into the calculator, I would recommend you try and pause in a moment, but and do that yourself. But when you plug this into the calculator, make sure that you're not multiplying by 10 to the 23. This is on the bottom. So you do 1.24 times 10 to the 24 divided by 6.02, press enter. Divided by 10 to the 23, press enter. Please pause and see what answer you get now. All right, so you should get 2.06 moles of methane. You should have had 10 to the 24 over 10 to the 23. And those almost cancel each other out. You should not be getting 2 times 10 to the 40 something here. Okay, next question. What if we had 3.2 moles of O2? How many atoms of oxygen are there? All right, so we have moles of O2, and for every mole of O2, there are 6.02 times 10 to the 23 O2s. But O2 is a molecule. We cannot stop here. We're asked how many atoms of just oxygen are there, not how many molecules of O2 are there. So, having molecules of O2 will now convert into atoms of oxygen. We know that for every 1 molecule of O2, there are 2 atoms of oxygen. Yeah, O2 has 2 O's in it, so there's 2 O's per O2. So we should get 3.9 times 10 to the 24 atoms of oxygen. Okay, so what we just did was we used this mole map. In the first case, we converted from molecules, a type of representative particle, into moles. To go from representative particles to moles, you just take your representative particle number and then multiply by this unit conversion factor. It gets rid of the unit of representative particles because it was on the top and ends up on the bottom, and it converts into moles. In the second problem, we converted from moles of a substance into representative particles, but then into atoms. We had a mole of molecules of O2. So to first convert from that to molecules, from moles of O2 into molecules of O2, we multiplied by 6.02 times 10 to the 23 molecules per mole of O2. And then to go into atoms, we went from the number of molecules of O2 into atoms of O2 by multiplying by this unit conversion factor, which says the number of atoms of oxygen per molecule of O2.